Hi, this is Stephen Hardy, Editorial Director and Associate Publisher of Lightwave. One of the companies making a lot of noise here at OFC and FOEC in San Diego is Lightwire. I'm here with the company's CEO, Vijay Albuquerque, and their CTO, Cal Shastri, to talk a little bit about what the company is doing. Vijay, could you explain your technology to us?
So Lightwire is a CMOS photonics company. Our core technology is CMOS photonics, but we take our technology to market in standards-based products. Our first product that we have introduced at OFC is the SFP Plus LRM module. That's the module that I have here in my hand. And what we have here is a demo setup. I will start off with the module, the 10 gig SFP Plus LRM. This has extremely low power dissipation, 400 milliwatts versus what is in the industry typically 900 milliwatts, less than half the power. Best-in-class signal integrity, outstanding signal integrity, a wide temperature range, -5 to +85 degrees C, and excellent receiver linearity. Okay, so we have the SFP Plus transceiver, the LRM transceiver here. What you see there is the IMAS diagram. And again, what you should look at carefully is the mass margin. We have 40% mass margin over temperature. And this is outstanding performance, driven very much by our CMOS MZI structure.
Now, certainly one of the points of differentiation for Lightwire seems to be its integration technology. Cal, can you explain the technology behind these devices?
Definitely. Okay, this is the first engine behind our products, and this is the what we call a CMOS optical chip. And what that does, it leverages the existing investment infrastructure and discipline of the CMOS IC industry to achieve the level of integration and the manufacturability as well as the performance that we are looking for. So we said, okay, what are the attributes that we look for in providing these kind of solutions? It has to have very low power, very low cost, very small size, for obvious reasons of cost, level of integration, scalability, and every which way you look at it. And this is what we call our SysCap structure, which is the heart behind our advantage over other ways of doing photonics in silicon. What we do here is that this is nothing but a MOS capacitor with particular structure. And what this does is that it changes the refractive index of silicon with maximum amount of charge injecting into into the path of the photons, right where the photon intensity is maximum compared to other approaches. As a result, we get the very, very efficient structure, very high bandwidth structure, and we can drive this with simple CMOS voltages of 1.2 volt, which is very important because not only you want to have the simplicity in the solution, but also very small size and power dissipation. And that is what we achieve by this one. To give an example, our power dissipation to drive this structure at 10 gigabit per second to do the MZI modulation of the light is less than 30 milliwatts. And that is significant advantage over existing, not only existing way of doing things, but also other people's approach towards the problem. And our size of the modulator is also very important. Our size of the length is less than 0.5 millimeters, less than 500 microns. This is the these are the two arms of the MZI modulator, the electrical representation. That is, this is the CMOS capacitors and the resistors, parasitic resistors. Driving these modulators is as simple as a CMOS inverter driving another CMOS inverter in the CMOS chip. No transmission line drivers needed, no analog functions needed. This is truly digital CMOS photonics. And as a result, we get this very good performance at very low power dissipation.
Thank you very much, Cal. The kind of integration that we've just heard about is one of the major trends in the optical communications industry, and it provides the opportunity for further innovation, lowering of cost, and improved performance. And I think we're going to be seeing more of this in the future. For Lightwave Online, I'm Stephen Hardy.